Alright, so we're currently in orbit right now, and our spacecraft is above sea level of 200,000 meters. Now, what does this mean? This means that we must add it to the radius of Kerbal in order to get our R1. Our R1 would be 800,000 meters, 200,000 meters above sea level, plus 600,000 meters of the radius of Kerbal. With that being said, since the simulation uses real-world physics, but it uses a little bit different values, we can figure out what is our speed. Now, using the circular orbit formula, v squared equals mu times 1 over semi-major axis, our semi-major axis being our radius, since it's the only thing that is added, so it's radius plus radius divided by 2. It's basically going to be 800,000 meters. With that being said, using this formula, we plug in all our values. The gravitational constant, we basically end up with 2100 meters per second orbital speed. With that being said, this means that we must do a prograde burn, so the burn in the direction of the orbital speed in order to change this to ellipse. With that being said, we're going to take this up to a point where the ellipse is about to start. We're going to start the burn, and I'll explain how we get the delta V1, which is our change in orbital velocity in order to get this ellipse. So I'll see you later. Alright, so now we came to the point where we have to do a first burn. So I am just adjusting my spacecraft to prograde, so be in the direction of the orbital velocity. So what we must do is we must first find our delta V1. So basically that is the change required in our speed at specific orbital, at a specific radius, in order to create an ellipse. This ellipse will then let us go to the specific radius that we want. So we want 400,000 meters above sea level. And with that being said, we're going to do another burn in the same direction as we did first burn, in order to put it back into a circular orbit. Reason for that is that this is the most efficient way to transport a spacecraft. It is also the quickest way to do it. And the only problem we come up with is, how do we find delta V1? Well, I will put up on the screen right now here all the calculation steps required to do that. You can feel free to look at it, but then I also have it in the description, so in engineering description that I made and that has been attached, and that will explain how I got the formula in the first place. But the only thing we need to know right now is that using the two formulas, I will show them right now up on the screen. Delta V1 and V2 we'll use after. For delta V1, we basically figure out that the delta V1 is 113.594 meters per second. This means that we have to add this speed to our orbital velocity. Our orbital velocity, by calculating, is actually 2100 meters per second. So in reality, when we're at perigee or any other point in the circle, we have to burn and increase our speed to 2213 meters per second. This will create the ellipse that we're looking for, that will have one radius to the point of 400,000 meters and one radius to the point of 200,000 meters. When we're at the top of 400,000 meters, we'll do another burn. And by looking at the screen, we can check that right now we're slowly burning to it, we're slowly adding speed, and I will show all the information needed right now that requires this burn. Alright, we'll see you back when we're at the apogee, which is the highest point. And that's when we're going to do the second burn. Alright, so now we're at apogee, preparing for our third burn. I'm about to throttle up, and what we have at apogee, using the formula for circular, I will show it on the screen how I got that. We figure out the speed that it has to be at apogee. The speed at apogee in this ellipse has to be 1771 meters per second. With that being said, this must add it to a delta V2 in order to get a circular orbit at 400,000 meters per second. Now, we figured the answer of the V2, or the orbital speed at 400,000 meters above sea level, is to be 1,878 meters per second. This means that whatever delta V we add has to be in relation to, it has to be at the end 1800 meters per second, roughly 1800 meters per second. We can of course just subtract that from VA, and we have V2, or we can use the Hohmann formulas if we don't know to solve for it. So here I'm showing the Hohmann formula, how to solve it. To quickly go through it, using it, plugging in the values, we will get the answer of 107.444 meters per second. This gives us the answer of 1,878.69 meters per second, which is exactly what we need. And that will basically complete our Hohmann transfer. And by testing it, I'll show you how close we get to it. And as we can see, we get about close to about 6 kilometers in difference of what we actually want. That is pretty close. It's about 0.25% error. In real world, that is not going to be that the spaceship is, or the people at the ground are not going to be that happy, because that requires another 6 kilometers of travel to wherever you need or to adjust. But it is the most perfect we can get simulation and using keyboard on the simulator. And that will basically conclude our Hohmann transfer, and that will conclude simulation. This basically proves that using the Hohmann formulas and using the calculator formulas, we can solve for delta V1, delta V2 required for us to burn in space in order to get it. And by the simulation, we can see that it does match up with little to no error. And of course, there's many different ways. There's faster ways, there's quicker ways, but the full way to do it is using the Hohmann technique. And that would be it for the simulation, and have a good day. Now, I tried to do actually another one going back, and we tried to do a more test that it will give us more exact answer. And by looking at it, we got the answer much closer. Instead of being 6 kilometers, we got the answer to be about 1 kilometer in difference. But of course, the speed is going to be a little bit different because we adjusted a little bit to it, but we got the orbit a bit better, in the better direction. And by conclusion means that depending on how you do it, we will get a better result at it. Since it is a simulation, it does take a good % error, but in reality we did a very good job of having about a 0.01% error, and that concludes this simulation to be a success.